We just covered sampling distributions where I tried to give you some intuition behind what a sampling distribution is and the main results about them, which I've summarized on this slide. Now, in that video, I stated these results without any proof. I'd like to spend a few minutes showing you how all of the formulas that we reviewed earlier this week will allow us to understand why these results hold. So let's go over to my paper. I think it's better to see this on paper. And so what I'm going to do is I'm going to assume that x1 through xn is a random sample. Now, what that really means is that these are IID. So what does IID mean? IID means independent and identically distributed. So each one of these x's is independent of each other. So if I'm sampling parts, the measurement on one part does not affect the measurement of another part. So they're independent of one another. That's going to be critical for us when we try to derive the results that I had on that on that slide. Let's just write out what they are. The expected value of any single xi has to equal some common mu, and the variance of any single x is equal to some common sigma squared. At this point, I'm not going to make any assumptions about the shape of the distribution. Perhaps they're normally distributed, maybe not, doesn't matter. Okay, so right now all I'm assuming is that they're independent and identically distributed. So the result is this. The total, which I think I called t hat on that slide, is just going to be, if I add up all these x values, x1 plus x2 plus all the way through x sub n. And then x bar is just our sample mean. So this is going to be x1 plus x2 all the way through, there's a plus sign in there, xn divided by n, or you can just write this as the total divided by n. Now, something that's really important to notice is that these are both random variables. Okay, so they are sums of a bunch of random things. I don't really know what these x's are until I observe them, and so I'm adding up a bunch of random variables, or maybe I'm adding up a bunch of random variables and dividing by n. Now, let me just write a theorem. So the theorem is the expected value of t hat is equal to n times mu. So why is that? Well, let's go write it out. So we could say proof if you like. The proof of this is that the expected value of t hat is just the expected value of x1 plus x2 plus all the way through x sub n. Now, I'm going to refresh your memory about some very important results that we had from back here. So if we go back to our probability theory results, the sum of two random variables is just the expectation of the sum is just you can just distribute the expectations across the random variables. So let's go do that. This is just the expected value of x1 plus ... plus all the way through the expected value of xn. So what's the expected value of x1? Well, the expected value of x1 is just mu, and then I've got x2, well that's mu, plus all the way through the end, which is mu. Therefore, this is equal to n times mu, and I've established the result. So if I observe n observations and I add them up, I just expect n times whatever the mean is. That's the mean of this total, is just n times the mean of a single observation. Now let's have another. Maybe this is not important enough to call a theorem, but what's the expected value of x bar? Let's go find that. So the expected value of x bar, if we go plug in our definition, so there's a number of ways we could do this. We could plug in this definition, or I've already written it out, it's t hat over n. Let's work with t hat over n. Now we're kind of back to a single random variable. So I have a random variable t hat and a constant n, and remember from last week, I can just pull that n out in front. So this is just 1 over n times the expected value of t hat. Well, what is the expectation of t hat? It's just n times mu. The n's cross out, and you're just left with mu. So what I said was, on the average, you get the true value. So across all samples, sometimes your sample mean will be too high, sometimes it'll be too low, but on the average, you're going to get the right value. That's what that result is saying, and that follows from these basic rules of probability. And so that's why I say these rules, E at AX plus BY equal E A at X plus B E of Y. That is one of the most important formulas from probability theory that we're going to have. Well, let's go on to the other results. So what about the variance? So I'm not going to write this as a theorem, I'm just going to derive it. So what is the variance of t hat? Well, we're going to go through basically the same steps. This is equal to the variance of x1 plus x2 plus all the way through xn. Now, what is this sum? Well, let's go back to the course packet, and I'm going to use my lemma, because what we have here is a bunch of independent random variables, so I don't need to worry about the covariances. And so that's why that independence up here was so important. So my constants in this case are all just ones, so I have to square ones, but I'm not even going to bother to write those. So because of independence, I can just distribute this variance sign. This is just the variance of x1 plus the variance of x2 plus all the way through the variance of xn. So notice I have n copies of this. This is just n times, what's the variance of any single xi? Well, it's sigma squared. So n times sigma squared. So that is my formula for the variance. I think on the slide, I expressed it as a standard deviation. So the standard deviation of t hat then would be sigma times the square root of n. So if we just take the square root of that, that's what I get. And that's a kind of an important result. Okay, now the last formula that I'm going to establish for us is the variance of x bar. So what is the variance of x bar? Well, using my definition of x bar up here as the variance of t hat over n, I can compute this. So how do I find the variance? Remember, I've got a constant. When I bring a constant outside of the variance function, it gets squared. So this is going to be 1 over n squared times the variance of t hat. Now, what is the variance of t hat? Well, we just found it to be n sigma squared. So this is going to be n sigma squared. Then I have that n squared over here. So let's write that n squared as n times n, if you don't mind. Then I can just cross out one n in the numerator with one of the n's in the denominator, and we're left with sigma squared over n. Now, we often are much more interested in the standard deviation. So what is the standard deviation of x bar? Well, it's sigma divided by the square root of n. So this is a very important formula, as is this. They're basically the same result expressed in different units. So let's go back to the course packet, and I'm not going to prove anything else here. We're not going to do the sampling without replacement formula. The proof is a little bit more difficult, and we need to remember some things about the hypergeometric distribution, which I haven't reviewed with you. I'm also not going to prove either of these results about the shape of the distribution. So if we add the assumption that it's normal, then both the total and the mean are exactly normal. I'm also not going to prove the central limit theorem. We would need something called a moment generating function, which you probably didn't cover in your first course in probability theory. So we're just going to take those at take those on faith and use them going forward. Okay, so the kind of the upshot of all this is you want to get really good with those formulas for the expectation and the variance of linear combinations of random variables.